For 38 years, planetary scientists taught a specific fact about Uranus that turned out to be wrong, not because anyone made a mistake in 1986, but because of something nobody could have possibly known at the time. In January of that year, Voyager 2 flew past Uranus and sent back data revealing a magnetic environment so strange, so lopsided, and so seemingly contradictory that it became one of the defining mysteries of outer solar system science, cited in textbooks, planetary science courses, and popular explanations of our solar system for nearly 4 decades afterward as one of the strangest confirmed facts we knew about any planet. In 2024, a team of NASA researchers went back through that same decades-old data and discovered the actual explanation. And it was not what anyone expected. Voyager 2 had not captured a typical day at Uranus. It had, by sheer chance, arrived during one of the strangest, most statistically rare moments in that planet's recent history, an accident of timing that scientists spent nearly 4 decades treating as the planet's normal permanent state. This is the story of how a single, decades-old flyby ended up teaching an entire field of science the wrong lesson about an entire planet, and what happened when researchers finally went back and figured out why, using nothing more than old records and a question nobody had thought carefully enough to ask before. To understand why this matters, you first need to understand exactly what Voyager 2 actually found at Uranus back in January 1986, because at the time, it was already considered one of the strangest results of the entire Voyager mission. Voyager 2 remains, to this day, the only spacecraft in human history to have ever visited Uranus, a distinction that has now stood for nearly 4 decades, with no successor mission, even under active construction. As it approached the planet, roughly 11 hours before its closest pass, Voyager 2's instruments crossed into Uranus's magnetosphere, the invisible magnetic envelope generated by the planet's own internal processes. On most planets with a working internal magnetic field, including Earth, that field behaves in a reasonably predictable way, roughly aligned with the planet's rotational axis and centered somewhere near its core, the same basic pattern a simple bar magnet produces. Uranus broke that pattern immediately and dramatically. Voyager 2's instruments revealed a magnetic field tilted a staggering 59 degrees away from the planet's actual rotational axis. And the source of that field turned out to be significantly offset from the planet's center as well, shifted by roughly a third of Uranus's entire radius toward one pole, an arrangement unlike anything measured at any other planet before that flyby, or in the decades since. To put that tilt in perspective, imagine a bar magnet embedded inside a spinning planet, but instead of that magnet lining up roughly with the planet's spin axis, the way Earth's own internal magnetic field does, it sits tipped over at an angle greater than the angle between a clock's hour and minute hands at 10 minutes past 3, and instead of sitting at the planet's center, it has been shoved noticeably off toward one side. Nothing like it had been recorded at any other planet before or since at Uranus's neighboring ice giant Neptune, encountered by Voyager 2 3 years later in 1989, or at any of the rocky planets or gas giants closer to the Sun. Compounding the strangeness, the region around Uranus appeared to be almost completely emptied of plasma, a near vacuum where scientists expected to find a reasonable population of charged particles trapped by the planet's magnetic field, the same way Earth's own magnetosphere traps particles and structures like the Van Allen radiation belts. And yet that same emptied region also contained radiation belts of extraordinary intensity, second in strength only to Jupiter's own, the most powerful in the entire solar system. Intense enough that they posed a genuine, carefully modeled hazard consideration for the spacecraft's own instruments during the flyby itself. Scientists studying the data were left with a genuine contradiction sitting at the center of their results, a magnetosphere that appeared to be simultaneously stripped almost bare of plasma and home to some of the fiercest radiation ever measured anywhere in the solar system, two properties that, under most theoretical frameworks describing how planetary magnetospheres actually behave, should not comfortably coexist in quite this combination. For the following 38 years, this contradiction sat in the scientific record largely unresolved, treated as simply one of the strangest, most fundamental facts known about an entire planet, discussed in textbooks and planetary science courses as a genuine permanent peculiarity of Uranus itself, a defining characteristic of the planet, rather than a temporary condition captured during one unlucky week. That began to change in 2024, when a team led by planetary scientist Jamie Jasinski at NASA's Jet Propulsion Laboratory decided to revisit the original Voyager 2 data with a very specific question in mind, one that nobody had rigorously pursued before: what was actually happening with the solar wind in the days immediately surrounding the flyby itself. The solar wind, the constant outward stream of charged particles blown off by the sun, does not arrive at any planet in the solar system at a constant, unchanging pressure. It fluctuates, sometimes dramatically, driven by activity happening on the sun's own surface, compressing or expanding the magnetosphere of whatever planet happens to be in its path at any given moment. The same basic principle that causes Earth's own magnetosphere to compress during periods of intense solar activity and expand again once conditions calm down, a well-documented phenomenon much closer to home that researchers have been directly monitoring for decades using instruments in Earth orbit. The specific challenge Jasinski's team faced was that nobody had a direct, independent measurement of solar wind conditions actually at Uranus during the Voyager 2 flyby, since Voyager 2 itself was the only instrument anywhere near the planet at the time. Instead, the team had to reconstruct likely conditions using a combination of measurements taken by other spacecraft positioned elsewhere in the solar system during the same window, and sophisticated computer models designed to propagate solar wind conditions outward from where they could actually be measured to the specific, much more distant location where Uranus happened to be sitting at the time. That reconstruction is itself a genuinely difficult technical undertaking, piecing together indirect evidence spanning enormous distances, and significant time delays, since solar wind disturbances take days to travel from the Sun's immediate vicinity all the way out to Uranus's orbit, nearly 20 times farther from the Sun than Earth itself. Piecing that reconstruction together, Jasinski's team found something that had never been properly accounted for in nearly 4 decades of analysis. In the days immediately before Voyager 2 arrived, the solar wind reaching Uranus had been unusually intense, compressing the planet's magnetosphere down to a fraction of its normal size. The team calculated that Voyager 2 likely encountered Uranus during a genuinely anomalous, compressed state, a specific condition of solar wind pressure that, according to their modeling, exists less than 5% of the time, meaning that on 19 days out of every 20, Uranus's magnetosphere should look meaningfully different from what Voyager 2 actually recorded during its single brief flyby. In other words, the single closest look humanity has ever taken at Uranus's magnetic environment, the only direct measurement we have ever obtained from any spacecraft at this planet, may have captured it during one of the rarest possible windows. A genuine statistical fluke mistaken for 38 years as the planet's ordinary, everyday condition, the scientific equivalent of judging an entire city's typical weather from a single afternoon that happened to catch a rare freak storm. The implications of that realization are worth sitting with directly, because they cut against something scientists generally try very hard to avoid, building an entire body of theoretical understanding around a single, unrepresentative data point. If Voyager 2 had simply arrived a few days earlier, before that particular wave of solar activity reached Uranus, the solar wind pressure compressing the planet's magnetosphere would have been roughly 20 times lower than what the spacecraft actually measured. A difference in external pressure large enough to substantially reshape the size, structure, and behavior of the entire magnetic environment surrounding the planet. Under those calmer conditions, the entire magnetosphere Voyager 2 recorded could have looked meaningfully different, potentially less extreme, potentially less contradictory, potentially closer to the kind of magnetic environment scientists might have expected from a planet with Uranus's known internal structure, based on models built from studying other, better understood planets throughout the solar system. Nearly 4 decades of scientific literature, popular science writing, and planetary science education had been built, at least in part, on a single flyby that appears to have caught the planet at an atypical, compressed moment, and there is currently no way to fully verify how different the results might have looked under more ordinary conditions, because Voyager 2 remains the only spacecraft that has ever been close enough to check, a fact that will remain true for at least another decade or two under any currently realistic mission timeline. This finding does not mean Uranus's magnetic field is not genuinely strange in its own right, and it is worth being careful not to overstate what the 2024 reanalysis actually overturns. The fundamental tilt of 59 degrees away from the planet's rotational axis and the significant offset of the field's source from the planet's actual center are considered structural properties of the planet's interior, likely tied to how convection currents move inside the layer of electrically conductive fluid, probably a slushy mixture of water, ammonia, and methane under extreme pressure that generates the planet's magnetic field in the first place, and these basic characteristics are not something a temporary compression of the solar wind would be expected to change, since they arise from processes happening deep inside the planet rather than from anything occurring in the surrounding space environment. What the 2024 reanalysis specifically calls into question is the more extreme, more contradictory details, the near total absence of plasma paired with unusually intense radiation belts, details that may have been substantially exaggerated, or even partly created, by the unusual compression Uranus's magnetosphere happened to be experiencing during that exact 1-week window in January 1986. Understanding why this distinction matters requires understanding what a compressed magnetosphere actually does to a planet's surrounding environment. When intense solar wind pressure squeezes a planet's magnetic bubble down to a smaller size, it can dramatically increase the density of charged particles trapped within certain regions, while simultaneously reshaping how radiation belts form and where they concentrate, effects that can produce exactly the kind of seemingly contradictory readings Voyager 2 recorded, an emptied plasma environment in one region existing alongside intensified radiation in another, purely as a consequence of external pressure rather than anything unusual about the planet's own internal magnetic generation process. Jashinsky's team argued that accounting for this specific temporary compression could resolve much of the contradiction that had puzzled scientists for nearly 4 decades, not by discovering some exotic new physical process unique to Uranus, but simply by recognizing that the single data point everyone had been working from was measured under unusual, temporary external conditions, rather than the planet's typical steady state. There's a broader lesson embedded in this entire episode that reaches well beyond Uranus itself, one that applies to nearly every distant object in the solar system that has only ever been visited once. Nearly every piece of direct, close-up data humanity possesses about the outer planets comes from a small handful of brief flybys, snapshots captured during a matter of hours or, at best, days, rather than the kind of sustained, long-term monitoring that missions orbiting closer, more frequently studied planets like Mars or even Jupiter and Saturn have been able to provide across years of continuous observation. A single flyby, however carefully executed and however sophisticated its instruments, can only ever tell you what conditions looked like during that one specific, narrow window of time. It cannot tell you whether that window happened to be typical or exceptional, calm or unusually turbulent, representative or a genuine statistical outlier, unless something else, some independent source of information about the surrounding conditions at the time, happens to survive long enough for later researchers to check, decades after the original data was collected, and the original spacecraft has long since moved on to somewhere else entirely. That is precisely what made this particular correction possible at all. Records of solar wind activity from January 1986, gathered by other instruments, entirely separate from Voyager 2 itself, scattered across various archives and datasets maintained by different institutions over the following decades, happened to survive in usable form for nearly 4 decades, allowing Jashinsky's team to reconstruct exactly what conditions actually looked like during that specific flyby window, long after the fact. Without that surviving, independent record, the anomalous compression affecting Voyager 2's Uranus data might never have been identified at all, and the planet's supposedly contradictory magnetosphere might still be treated today as an unquestioned, permanent fact about Uranus, rather than what it now appears to actually be, a snapshot of an unusual, temporary moment mistaken for decades as the ordinary state of an entire world. It is worth appreciating, too, just how much patience this kind of correction actually requires. Nobody discovered this compression by accident or in a rush. It took a dedicated research team, decades after the original flyby, deliberately setting out to ask a question nobody had asked with quite this level of rigor before, and then doing the painstaking work of reconstructing solar conditions across billions of miles of space using fragments of data never originally intended for this exact purpose. This discovery carries direct practical weight for how planetary scientists are currently thinking about future missions to the outer solar system. A dedicated orbiter mission to Uranus, capable of studying the planet's magnetosphere continuously over months or years, rather than during a single, brief pass, has been proposed and studied by NASA, identified by the planetary science community as one of the highest priorities for the coming decade of solar system exploration, precisely because a sustained mission could finally distinguish between what is genuinely, permanently strange about Uranus and what was simply an artifact of unlucky timing during humanity's only visit so far. Until such a mission is actually approved, funded, and successfully makes the multi-year journey out to Uranus, the correction identified in 2024 stands as the best understanding. Currently available, an important hard-won reminder that even data collected by a spacecraft as reliable and as thoroughly studied as Voyager 2 can still, decades later, turn out to have been telling us something subtly different than what generations of scientists originally assumed, simply because nobody had yet gone back and asked the right question about what else was happening in space during that one specific week in January 1986. If this is the kind of story you want more of, subscribe and let me know in the comments what other decades-old space data you think might be hiding a similar surprise.